All right, welcome to this video. We're going to be going over 3.3, and that's it for today. So 3.3 is on analyzing graphs of quadratic functions. And let me share my whiteboard here. There we go. Okay. All right. I can't get rid of this thing. There we go. Good. Okay. So we're going to start with functions of this form. So f of x equals a times x squared. Let's see. Not there. Let me get back to the first. Yoink. There we go. This. Plus k. So let me see if I can maybe write that better. I don't know. Maybe it doesn't matter. But it's a multiplied by, in parentheses, this x minus h that gets squared. And then I have a plus k on the outside. So we've talked about transformations of graphs. This is a transformation of the graph f of x equals x squared, right? Some of the transformations that we've talked about are if I have, say, x squared plus k, I'm just going to say, right? Then this k, let me get rid of this gold color. I don't like that very much. Yellow, is that better? If it's some function, then I just add k to the end of it. This is a vertical shift. Right? Likewise, if I have something like, say, x minus h squared, so I'm changing the inside the actual function itself, this h is my horizontal shift. And then if I have, scooch this up a little bit. If I have, let's go red perhaps, ax squared, right? So I'm looking at three different things here. I've got a vertical shift if I just add a k to it. I've got a horizontal shift if I subtract h inside the parentheses, inside the square. But if I just multiply in front by an a, this is a vertical, either a stretch, right? Remember, if a is bigger than 1, then it's a vertical stretch. If a is between 0 and 1, then it's a compression. If a is negative, then it is a flip, and then also either a stretch or a compression, right? So I have those options there, stretch or compression. Right? But over here, I have all three of those things happening at the same time. I have my vertical stretch or compression. I have my horizontal shift, and then I have my vertical shift, right? All three of those things are happening. So that's really all that I have to do with this graph is take x squared and then change it based on those three things, right? So we're going to do that. We're going to take a look at, let's say, this. Oops. And we want to graph perhaps. I can't use squares, so I'm going to go back to the pen here. Let's graph f of x equals 2 times x plus 3 squared, and then minus 2. Right? So if I go to graph this, I'm going to look at my moving left and right, up and down first, right? So these two things right here, right? The plus 3 on the inside means I'm going to move it to the left 3, right? So this is a left by 3. And then this other one here tells me that I'm going to shift down 2, right? So if I ignore this 2 for now, we'll come back and look at that and what happens here. For right now, what I've got is a left shift by 3 and then a down shift by 2, and I can do that pretty quick and easy. And I'll do this in stages. X squared looks like this. The shift left by 3, I'm just going to click over 1, 2, 3, and then down 1, 2. So this point right here is now shifted over 3 and down 2, so it's now here. And everything else gets shifted in that direction with it. And so you'll see that my graph right now looks like this. Oops. Right, something like that. But this is not the complete graph. This is x plus 3 squared minus 2, right? That's taking into account the shift, the left shift, the down shift, but not that stretch of a factor of 2. But from where I'm at, I can treat that we call this point right here the vertex. That is going to kind of stick where it's at, and that vertical compression is going to pull up from there. So everything gets kind of stretched. And so my final answer, let's go with, where's purple? I like that one. Let's do this. So everything gets stretched up by 2, so it just kind of gets whoop and stretched up. Just like Laffy Taffy pulling it, it just gets stretched, right? So this purple one is my 2x plus 3 squared minus 2. That's my final answer. Right? And if I want to graph, let's say, oops, f of x equals, let's go negative 1/2 x minus 1 plus 3. Okay? So once again, I've got kind of those 3 things happening, but really I have a 4th thing because there's a negative right here. So the negative means that everything's going to be flipped about the x-axis, right? And then it's going to be compressed by 1/2, right? So it's going to be squished in. And I've got the move to the right 1 and up 3, right? So I've got to flip about the x, about the x because of the negative. I have a compression by a factor of 1/2. Right? So I have those 4 things happening, but I can do it, right? Once again, if I just look at what's happening, this is an x squared graph that just goes through those 4 changes. And so normally, if my graph would look like this, right, I can do that compression first. It's sometimes easier to do the compression first rather than moving it and then stretching or compressing. But this is just my regular x squared. If I compress it, everything just kind of gets flatten down. And so a value up here, this value is only half as much. This value up here is only half as much. And so it really just kind of widens the base of this parabola. Right? It's been smushed. So this is 1/2 x squared, right? I need to flip it, right? That negative says flip that sucker down, and so I will. So I flip it down here, the wider parabola. Oof. Something like that, right? So now I've got negative 1/2 x squared, right? But now I just need to take care of the shift. And if I take this and shift it to the right by 1 and up by 3, that's it. That's my graph, right? So this is a little hairy. I'm not going to throw that on this axis. I'm going to create a new one, a clean one here. So I'm taking this orange one here, and I'm going to shift it to the right by 1. So it comes over 1 and up 3, 1, 2, 3. So my vertex is here. It's still that wide base, and it just looks like this. Yeah, and that's my, that's the graph of that function. So you'll notice here, if you, as you do a few of these, that if, excuse me, this number in front is positive, it's going to open up. And if the number in front is negative, it's going to open down. So in general, if I have the function f of x equals ax minus h squared plus k, if a is greater than 0, then this thing opens up. But if a is less than 0, it will open down. And then each of these values, that each of these graphs has this vertex that I've kind of pointed out here. The vertex here is that highest point. If it's a parabola that opens down, the vertex is the highest point. If it's a parabola that opens up, then the vertex is the lowest point, right? And so the vertex in either case is going to happen at the point h comma k. So that's kind of nice if you have a function that you're trying to graph. So if I have, let's say, f of x equals whatever it is, right? This vertex is at the point 7, -4, right? And it's 7, not -7, because the equation here has a negative on the inside, right? So minus, well, that makes h7. But the k is a plus out here, so if it's negative, then that makes your k value negative, right? So watch your signs there, and follow this, the minus and the plus here. Okay. All right. If I have this, but I have something like this. Let's say x squared plus 10x plus 23. Right? It's not in that form, but I can get it to be in that form if I want to. So we're going to do this by completing the square. And we've talked about this before. what we're going to do, instead of when we completed the square before, we shoved the last number off to the other side of the equation, but we don't want to do that here because I don't have this thing set equal to 0. So what I'm going to do instead is just rewrite this as x squared plus 10x plus, and I'm just going to put this plus 23, just scoot it out of your way. It's still on the same side as the x squared and the 10x, but it's out of my way, right? And so I'll complete the square by taking that middle number, dividing it by 2. That gives me 5, and then I take that 5 and square it. This is the number that I want here. So I'm going to write plus 25. But now I'm not dealing with a number on the other side, so I can't add 25 to the other side of the equation. But what I can do is add 25 and subtract 25 from the same side of the equation, right? Because now I've added 0. That doesn't change anything. But what it does is it gives me a perfect square right here. And then the rest of the junk, whatever you want to call it, it's just the leftovers, basically. But if I factor that perfect square, this then becomes x plus 5 squared. And then that's just minus 2. And it's now in that form, right? The junk becomes your k value, essentially. And so I know this is a x squared function who has a vertex at the point -5, -2, right? Negative again because I have to watch my sign on the inside, and then I use the same sign on the outside. Okay. So fine, did I say to graph that? I did say to graph it. So let's graph it. Let's throw this up here. I know the vertex is at -5, -2. So 1, 2, 3, 4, 5, -1, 2. And that's going to be my vertex. I know this is just a parabola that's going to open upwards. There's no stretch or compression. And so it's just a regular old parabola that just goes, oh, well, I kind of open that wide and then narrow on that side. But it's a parabola that goes right there. That's maybe better. Maybe, maybe not. I don't know. But that's it, right? Let's do this guy. In fact, let me start with not that one. Let's do one with a 2 in it. So we didn't deal with anything like what you're about to see. If you've watched any of the Khan Academy videos, you might have run across this. But what we're going to do is complete the square when in front of this x squared, I've got this not 1 sitting there, right? So it's just a little bit different. You have to be a little careful with what you're doing. So let's do it. I'm going to start by, again, I'm just going to shove that -3 just out of my way. I don't want it near me. Just move over there until I'm done, and then we'll pick you up when we're ready, right? And so I'll just rewrite this as 2 times that x squared plus my 16x and -3. Just scooch. Get out of here for a minute. Right? But now with my x terms, both the x squared and the x term, I'm going to factor out this 2 from both of those. And so I've got a 2 on the outside here. This is x squared plus now 8x. And I'm not going to include this minus 3 in that factoring for obvious reasons here, because it's not divisible by 2, but I just don't want it there. Just stay out of my way for a little bit until we're done, right? Now what I want to do though is complete the square inside here. So I'm going to take that 8, divide it by 2, gives me 4. And then 4, oops, I can't see where I'm at here. I gotta lean. That 4 gets squared and gives me a 16. Okay. And that's what I want in here. Let me just give myself a little bit of room here. And I want that in here, so I'm going to add 16. But I'm also going to minus 16. I'm going to make sure that I minus it inside the parentheses, right? Because if I add 16 and subtract 16 inside that parentheses, then inside the parentheses, I've added 0, right? But the completed square, the nice, beautiful little square, is this stuff. And I want this 16 out of there. How do I get the 16 out of there? Well, I would have to distribute this 2 through everything, kick the 16 out, but I'm going to refactor that 2 out of those first 3 terms. So really all I'm going to do is take the 2 and multiply it by the negative 16 in order to kick it out of the parentheses, right? So this 2 is still going to be here in front of these 3 terms. But I'm kicking out the minus 16 by multiplying it by 2. That becomes negative 32. And then minus 3 more. Now what I've done is I have this nice, perfect, little perfect square right there. So I have that 2 hanging out in front. Inside there, I have x plus 4 squared. And then on the outside, I have minus 35. And that's it. Where's my vertex? The vertex happens at negative 4, negative 35, right? This is there's a positive number in front, so it's a parabola that opens upward. There's a vertical stretch of 2, so find that vertex, stretch it by 2, and just throw an x squared there, and you've got it. So the graph of this looks like it's going to be not, labeled very well, but let's say that this is negative 35 and negative 1, 2, 3, 4. My vertex is there, and then it's just a narrow because it's been stretched by a factor of 2 in the vertical. Right? Okay, let's take a look at another one of those with a number in front, but this time let's call it let's say we have f of x equals, I'm going to do this example here, 1/2 x minus 4x plus 8. Okay. So now I've got this 1/2 sitting here. I kind of don't want it there, but let's go through the process. First thing I want to do is tell 8 to go sit on the sideline for a minute. Then just with these two terms, you can group them like this if you want to, but I want to pull that 1/2 out. So I'm factoring out a 1/2, which is to say I'm dividing out a 1/2. And so that leaves me with x here, but it leaves me with minus 8x. right? And if you're not sure why, think about what it means to divide 1/2, right? Not divide by half, but divide by 1/2, right? Ever so slightly different wording. And I'm going to leave some room, and then I've got this +8 that I didn't let participate in the factoring. But now this x inside the parentheses is just that's an x, sorry, these should be x squareds, I'm sorry. Squared, squared, squared. My x squared term has a 1 in front of it, so I can complete the square. Half of -8 is 4. Square it gives me 16, so I'm going to add 16 and subtract 16 at the same time. But I'm going to kick this -16 out of here by applying the 1/2 to it. So the 1/2 doesn't get distributed through all of this junk. But I'm just going to kick out the -16. If I have -16 times 1/2, that is -8. So then I have 1/2 multiplied by the perfect square here ends up being x minus 4 squared. And this +8 and -8, that goes to 0. So there is no plus or minus anything on the outside. But I can think of that as simply a +0 if I want to, which tells me then that my vertex is at the point 4, 0. And then this is opening upwards with a vertical compression of 1/2. And so if I find 4, 0, 1, 2, 3, 4, there's my vertex. It's going to be a wide one because it was multiplied by 1/2. And there we are. That's the graph. All right. There's a pretty hairy one right here, so let's do it. Let's get me some clean area here. Let's say I have some function, right? And they don't all have to be f's. Let's call this h of x. But this guy is -2x squared plus 10x minus 23/2. So right off the bat, yuck, it's got fractions in it from the get-go. But I'm going to go through the same process, right? I'm going to start by kicking that -23/2 just off to the side. It's still there. It's still part of the line. But, you know, go away. Go to the kids' table for a bit. The adults have some stuff to do. And then I'm going to factor out -2 from both of these terms. And so to factor out a -2, that leaves me with an x squared, but now it's minus 5x. Once again, if you're not sure why that is, it's because we're dividing out that -2. And so 10 divided by -2 is -5. Or if you like to think of it this way, if I redistributed this back in, -2 times -5 gives me that +10. Leave myself a whole bunch of room for those parentheses, and then minus this 23/2, still sitting at the kids' table. But I can complete the square here, but that number is not divisible by 2, so I get this -5/2. I can't simplify that, but I end up squaring that to give me 25/4. Right? That's what I want to add here. And then I also have to subtract it, otherwise I'm changing the function. Once again, I want to kick this 25, the -25/4 out of here, but in order to do that, I have to distribute the -2 with it. So I will, when I do that, that gives me the -2 out in front of the 3 terms that I'm not going to distribute it through. But this minus 25 over 4 multiplied by negative 2 turns into a plus, and it's just 25 over 2. But then I have minus 23 over 2, so that's actually a nice thing because that gets rid of this fraction on the outside. This turns into plus 2 over 2, which is 1. On the inside of the parentheses, though, that's a nice little perfect square. It's not beautiful, right? But this number before we square it is always going to be the number on the right-hand side of the square. And then, of course, I have that minus 2. And that's it. Therefore, I know that I have a vertex at positive 5 over 2, comma 1. I know this opens down. And I know it's stretched by a factor of 2. And that's it. That's this function. If I wanted to, I could graph it. I think we're all getting sick of my artistic abilities, but yoink, yoink. Just find the point 5 halves and 1. So that would be like right there. It opens downward, stretched by 2, so it's going to be a thin one. So it should look something like that. Okay. If I have my parabola written in this form, for the parabola in the form f of x equals, if it's all worked out, it hasn't been completed the squared, it's not in that nice form. If it's in this form, ax squared plus bx plus c, right? The vertex of this, if we were to go through and figure out the, like throw into the quadratic formula, right, we could do that. Or we could go through and complete the square, which is essentially creating the quadratic formula. But the vertex of this parabola is the x value is negative b over 2a. And then the y value is just that evaluated there. So the function evaluated at negative b over 2a. Right? So that is to say my x coordinate is negative b over 2a, but my y coordinate is the function evaluated where that x value happens, right? There's no magic formula for the y value here. You just plug in whatever you get for the x value into the function, and that's where your y value is, right? So let's see that in action. It looks weird to see it in general. Let's do it on this. So I'm going to specifically say, please use this formula above, because otherwise you could just complete the square, and that's totally acceptable unless you're specifically told not to, right? But using that function, we want to find the vertex of f of x equals negative x squared plus 14x and minus 47, right? And this 47 doesn't really matter, because if I take negative b over 2a, negative b is negative 14. A is negative 1 because of the negative there, so just negative 1. But this ends up just being negative 14 over negative 2, but that is just a positive 7, right? So in this, we're looking for this, negative b over 2a, comma, the function evaluated at negative b over 2a. This 7 is the x component of that vertex, right? To find the y value, I just take and evaluate f at 7. So I just plug it in. This is negative 7 squared plus 14 times 7 minus 47. So 7 squared is 49. This negative is hanging out on the outside, so it doesn't participate in the squaring, so it's still there when it's all done. That gives me negative 49. 14 times 7 is 70 plus 28, so 98, right? And then minus 47, right? And so when that's all said and done, there's going to be a difference of 2 here. I mean, that all, well, what I mean is that all collects up and ends up being 2, right? And so that's it. That's my vertex, is this is the y value. So that vertex happens at 7, 2. And so if I were asked to graph this, I could. I just find 7, 2. Since in the function, the a is negative, then it's going to open down. And there's no stretch because that x squared doesn't have a number other than a 1. It's negative 1, which makes it down, but it's a 1 in magnitude, so it doesn't stretch or compress, right? And so I should know what this looks like. I'm going to still this. Application from the book. Here we have a landscaper has enough stone to enclose a rectangular koi pond next to an existing garden wall of the Englishman's house with a 24 feet of stone wall. If the garden wall forms on one side of the rectangle, what is the maximum area that the landscaper can enclose, and what dimensions of the koi pond will yield this area? So let's draw a little picture. He has an existing, there's an existing garden wall of the Englishman's house with 24 feet of stone wall. So the garden wall forms one side of the rectangle, right? So here's the garden. It already has a big fence on it, right? So he really only has to create, he wants to make a rectangular koi pond. He really only has to do 1, 2, 3 walls, right? He has total of 24 feet. So I'm just going to call this X. And if that's X, since it's a rectangle, that is also X, right? So what is this over here? Well, he's only got 24 feet that he can work with. He's already designated X here and here, so that's 2 X's. So I've already lost 2X, right? And I don't know what X is, but in this graph, whatever X is, I have to subtract off 2 of them. And that's what's left over for that third wall. So I'm going to just erase this. And I'm going to write this as just 24 minus 2x. Now we're trying to maximize the area, right? We want to make this as much two-dimensional space as we can. That area is given by the function length times width. And so in this case, one of those values is x, and the other is 24 minus 2x, right? But if I distribute the x, this becomes 24x minus 2x squared. And I can think of this as being negative 2x squared plus 24x. Right? So what I want to do is figure out how to maximize this area, but what I have is a parabola, right? Because it's an x squared, this makes it a parabola. Because there's a negative right there, that means that it opens downward. But if I have a downward opening parabola, then the vertex is the highest point. Or the highest value of that function. So all I really need to do is figure out where does the vertex happen, and then I'll evaluate that vertex, and that is the maximum area that I can get out of this garden pond, right? So let's do this. Negative b over 2a is negative 24 over 2 times, well, a is negative 2. So that's negative 24 over negative 4. That is a positive 6. So then what is the greatest area? This is where it happens. To let x equal 6. But what is the area? The biggest area that we can have is f evaluated at 6. And so I just plug it in into either any one of these. It doesn't matter. They're all the same equation. So I'll just plug it into the last one. Negative 2 times 6 squared plus 24 times 6, right? Or negative 2 times 36 when I square the 6. And then plus I can multiply these. 6 times 24 is 120 plus 24. A dozen. And then 2 times negative 36 is negative, right? Negative 72. And so I have 72 square feet, right? We want the units, square feet. But that's the maximum garden pond or koi pond or whatever it was that we were doing, right? So then the question also asks, what are the dimensions of the pond? So we figured out x is 6. We figured out the greatest area that we could get is 72 square feet. But the dimensions here, we already know one of them. X is 6. So that's one side of the pond. But the other one is 24 minus 2 times 6, or 24 minus 12. And so that is 12. And so that's everything they could possibly ask us. What are the dimensions of the pond? 6 by 12. What's the maximum area? Well, 6 times 12 is our 72. That's it. That's the best that we can do. Let's do this one. Oops. All right. A model rocket is launched with an initial velocity of 100 feet per second from the top of a hill that is 20 feet high. Its height in feet, t seconds after it has been launched, is given by this function. S of t equals that. Determine the time at which the rocket reaches its maximum height and find that maximum height. So again, this is a parabola with a negative a value, which means it's going to open down, which means that maximum value happens at the vertex, right? Other applications might ask you to find the minimum, in which case your parabola should be opening up, because otherwise there is no minimum, but then that vertex would be the minimum. Here, it's opening down, therefore we have a maximum, right? So the question is, determine the time at which the rocket reaches its maximum and then find the maximum height. So I'm just going to go with, in this case, my variable is t. So that is to say that t is negative b over 2a. But negative b is negative 100 over 2 times a, which is negative 16. Or I have negative 100 over negative 32. The negatives cancel out. This ends up being 3 and an 8. Yep. So that's when, right? When does it get to its maximum? At 3 and an 8 seconds, or 3.125 seconds. But then it also says find the maximum height. So that is to say, find f of 3.125. So I plug it in. I've got negative 16 times that 3.125 squared plus 100 times 3.125, and then plus 20. 3.125 squared is, I don't know. Okay. Yeah, I knew it was coming, but this is 9.765625 plus 100 times that is 312.5, and then plus 20. On this guy, negative 16 times the 9. Oops, that's not what I wanted. Is 156, and it's negative, so negative 156.25 plus 312.5 plus 20. At the end of the day, when I combine those all up together, I'm going to get 156.25 plus 1, so 176.25. And that is the maximum height that the rocket achieves. All right. Let me just make sure. Yes. All right, so that's it for 3.3. We'll call that good. If you have questions, I'll be on during the last 20 minutes of the class as usual, and during my office hours. So yeah, thank you and take care.